Hello and welcome to Rudy's Electronics Lab. In today's episode I'm going to talk about two measurement devices that recently came on my way. It was actually one of my viewers that alerted me on one of these units being on sale. And it kind of attracted my attention, and you'll probably see later on in the video why that was really the case given the earlier topics I've been talking about. And actually, as a matter of coincidence, just a couple of days later, a second unit was being put on sale. And that second unit was actually just 500 meters away from where I was living. And when I went to pick it up, the unit was there in a truly gigantic suitcase full of all type of additional stuff. So it was not only the unit and a whole load of documentation and calibration reports of everything, but also coming, for example, with a number of different telephone handset hooks with some rather interesting type of cabling that I kind of never saw before. We'll get into that in a moment. Some cabling of unusual type of sizes. This looks like a jack connector, but not a type of jack connector that I ever used before in my life. We'll get to all of that in a moment. And quite importantly, the unit, or units I should say, also came with a number of additional interfaces with it. You see them over here. I'll explain you in this video that these interfaces play a quite important role in the life of this type of device here. Actually, when I just got my unit, I got a little bit shocked because I'm living in Europe, but the unit was set on 110 volts. And it's quite clear that this unit will not survive 220 volts if it's set to 110 volts. It really got a classic linear power supply and not anything like a modern switching type of power supply. So I carefully changed the voltage of the unit. I powered it on, and to my surprise, it was still working. And later on I actually found out what probably was the reason why this unit was still working, because between all the orientation documentation I had with the unit, there was one particular paper here, a shipping tax shippers export declaration, and actually the unit that I bought here was actually in Europe, but it was shipped to Flugplatz Ramstein, so it's the American NATO army base, and I know they have a 110 volt grid over there, so that's probably the reason why my unit was set to 110 volts. But at least I got it working well. It also came with a number of PCBs that were optional units with the device. Later on, when I installed all of it, I realized that it's probably never been installed before. It was like brand new, because much of the fittings were not there exactly in place, etc. I really had the feeling that these accessories have been there all the time and never actually been mounted into the device. There was also a bit of restoration going on with the unit, but now they are both working fine. And in this video, I want to explore a bit how the units are working. So let's get started and explore a little bit what these units really are about and who is making them. So the maker is Telecommunications Technology Corporation, TTC, a company that I myself never heard of, but they completely specialize in this type of telecommunication tester, bit error rate testers and generators and analyzers and the like. And it's a company that later had several different names, and I think it changed ownership also a number of times. It came under the name Acterna. Some of my papers say Acterna, Dynatech, GDSU, VEA, VI. I don't know. There were many changes over time, but they're still operating. I will quickly look a little bit into the different units or the different type of instrument that this company has made over time and apparently is still making. So the unit that I got over here is the Fireberd 600, with bird, I guess, for bit error rate testing as a bit of a joke. It's a device from halfway the 1990s, was on the market for about 10 years, and during that 10 years we had quite a lot of updates. So there were new interfaces being introduced. I think in the end there are almost 3 dozen of different interfaces, how you can actually use this device in an environment. There have been updates to the software. Everything is very nicely documented actually with the manual, the update manuals with each of these software updates, and it was a fairly successful device. Reportedly, of, well, not only this unit but the Fireberd series, they sold at least over 30,000 units of them, and that's also the reason why they're offered quite frequently on eBay and the like, and the units are not very expensive, and many of them I think are still in good condition. They're really well built. Actually on the inside they are really completely full of PCBs. I think I counted over 12 PCBs in each of these machines. It's a really very full machine here. There's several versions available of the machine. There is a metal case unit, there is a plastic unit called the 6000, there is a plastic unit called the 6000A, and that's the unit that I got over here, and there seem to be slight differences between them. One way you can recognize them, I think, is the A unit does not have a power switch on the front side, but it has it on the back side. And the A unit also has a connection for a analog measurement lid. That's something that goes in the lids here. I took them off, but a plastic lids here that open so you can easily protect it when you're traveling with the unit around. There's a bit of ambiguity between the A model and the regular model, because both the data sheets and the manual are not very clear about what machine that they're actually talking about. And there is actually also another version which is a unit without any control I/O buttons on the side, which is completely remotely controlled. And later when we look at use cases of this device, this does make quite a lot of sense, because one of the typical use cases is that this device is standing at different places in the network and you're controlling them remotely. Okay, so Fireberd is part of, or the 6000 is part of a whole series of devices. I got a quick overview here of the different type of devices that I eventually was able to locate on the internet. On the left bottom we actually got the device I got right here, the 6000, or I should say 6000A in this case, one with a printer in it, and later I'll talk also a little bit about the printer options of this device, because there are some interesting parts to that as well. There are also other series of devices by TTC. There's also the Interceptor series, which are devices that look fairly common to them, but they're basically really designed for intercepting traffic, a bit different from the typical type of bear testing that this device was made for. But there's a wider range of devices that TTC is making, also more modern devices, and some of them are the T-Bird series. I guess that should stand something for Thunderbird, and then we're not talking about the Thunderbird car by Ford, and we're not talking about the famous Thunderbolt guitar by Gibson. No, we're talking about the Thunderbird device by TTC. And so these are basically devices for Ethernet and fiber optics. So here we see a couple of older versions. You might still recognize a little bit of the design language of the devices over here. But there are a lot more modern devices as well. For fiber optics, many of them, some of them going all the way to 622 megabits a second. So that's the ATM, higher layer type of services, and yeah, so there's a whole lot of whole family of equipment that actually relates to the device that I got over here. Now I would like to talk a little bit about how this device is being used in a testing or telecommunication environment, and actually quite a couple of different type of use cases. So the use cases are basically in the laboratory, when the device can be used for designing, but also for testing a suspect type of device that you take out of a network and you do testing on whether there's something wrong with it. But the most important application was probably being used in a live network, being in the local loop of a telecom network, in the trunk line, so the lines basically between the central offices, or end between the two user locations at the very end of the network, and many of the device features are designed actually to be working in that way, in the sense that the device can really operate in a live network while there's actual traffic going through that network, and the device is just taking a little bit of that traffic, like one single time slot or so, and actually doing testing on them while the other traffic in the network remains. And that could be, yeah, like I said, trunk lines between central offices, it could be micro dish lines, etc. It could be satellite connections, as I pictured in this the video over here. And the way that you insert it in the network is manifold. And here you see a little picture of how they put that into their data sheet, all types of places where the device basically would be at home. And you can see that back in the whole design of the device, as well as the interfaces and yeah, and the manual, where they describe quite extensively how you should be doing all of that. Now let's talk a little bit about the different interfaces. I already told you that we got a bunch of different interfaces that came with the machine as I have it here. Actually, one of the interfaces I ordered separately later. That is the lab interface, and the other interfaces somehow came with the units that I acquired. But this is certainly not all the interfaces that TTC has been making. TTC has been making something over like 25, maybe 30 different interfaces. You see a bit of an overview here. Kind of summarizing this all together, because there are really a lot of interfaces, it might be hard to follow. I put them in a number of different categories. And so we got the first of all, we got the global trunk interfaces, the E1 interface by CCITT, later ITU telecommunications, who standardized those. We got the US trunk lines of slightly lesser capacity, 1.5 versus 2 megabit a second on the line, standardized by AT&T and Bellcore. We got the later ATM type of protocols. We got leased lines and local loop protocols. We got data protocols, more serial types of interface, UART interfaces like RS-232, all in the correct voltages and whatever, but also many other variants, and also a number of military type of data protocols, and all the ITU-T protocols with enormous connectors, and I'll show them later. And we also got a number of specialty type of cards, of which I think the TTL interfaces are the most interesting, because that's probably what you want if you want to use that in the laboratory. Now, turning to how the unit works inside, we can take a brief look at the block diagram, as I kind of reconstructed it from a couple of weeks of use of the device. So basically speaking, the device can be seen as a pattern generator that sends information to the plug-in interface, an analyzer where the information from the plug-in interface comes back into the unit. And both of them are running a certain pattern to generate it and to recognize the same pattern on the other side. And the plug-in interface, that's in the back side of the unit, and that's basically where the communications with the device or the network under test is taking place. And typically, except one or two exceptions, the plug-in interface also have a self loop, so you can use the Fireberd itself just to do testing without having any network type of attach. That typically happens with relays or so that are part of the interface units. Now, going one step further in complexity, we can also see that depending on the options that you have with the device, you can have a jitter generator, so the clock and data signals are going to suffer somehow from instability type of things, internally generated or externally modulated jitter type of signals. There's also a jitter analyzer that can analyze the characteristics of the incoming jitter. You can of course do that in the self-loop mode, and then you just see self-generated jitter, but of course that is more meant to be used in a complex network setting where you're afraid that something else in your complex network is increasing perhaps unacceptable amounts of jitter. And then going a little bit step more advanced as well, we can also see a little bit how the clocking of the device is arranged, because we got an internal clock that we can set typically I think to 15 megahertz or so. We can have a clock coming from the plug-in interface. In some cases that is interesting in some use cases, and some of the interfaces therefore also have an external clock input, and also the device itself has a universal external clock input. And so that is about generating data signals. And then on the side of analyzing these data signals, you can either take the clock that comes in from the received data from the interface, because obviously there might have been delay on the network and you want to capture the incoming type of clock signals. But optionally you can also have a clock recovery unit, which is recovering a kind of a clock from an interface form where you don't have the clock available to you. And yeah, you can switch between that for the analyzer. Now the unit has a large number of additional test points on the back, which I really like. You can just use like a little clip or so to connect it to the back, and I will be using that in the videos in a moment. And actually we can relate all these test points pretty nicely to the block diagram that I just showed to you, because here are basically all the places in the device where you can measure the signals going in. There's really almost everything that you could hope for in terms of a device. You can really follow what's going on in the device. The only thing that I think is really lacking there is a stray type of data input, but I'll get back later to it in the end of the episodes, when I'll talk a little bit about the strength and the weaknesses of the device. Now let's talk a little bit about the different interfaces that I got over here and what they are doing. And so the first interface that I got here, and actually I got two of them, and for the type of testing that I wanted to do, I wanted two of them, is the European E1 trunk line, so 2 megabit interface. With up to 32 telephony channels in there. It typically runs over a coaxial type of cable, but you can also do it with separate type of connectors. And don't be mistaken, these units are quite complex on the inside. Each of these units, well, they're very little bit in complexity, but here you see, for example, this European E1 unit being opened, and it's sandwiched two PCBs which are pretty full of advanced type of components, and with a little joke as well on the silk screen. Second, I got two versions of the US T1 adapter, and also note here we got like the other one, we got a telephone jack on there, and later we'll be using that type of thing. We also got a number of balanced type of separate connections here. And interesting, it uses a number of connectors that I have not been really using here before in the lab. And so some of them you see here, this is a jack connector, but this might be actually the source of jack connectors, older than the regular type of jack connectors that people know right now for music, like the 3.5 millimeter and the 6.25 millimeters. I don't know the name in inches. We can look it up. But this is known as the Bantam connector, a 4.4 millimeter connector, and I think it originally came from the mechanical telephone switches where the operator would actually connect a call through. 4.4 millimeter, and also the shape is slightly different from the regular type of jack connector as we know now. So that goes into some of the interfaces that we got here. Now here we got some more of the serial interface. I don't want to be spending too much time here, but there are a couple of interesting things about here. This complies to a number of regular serial protocols, but also US military type of standards. And if you look very well at the connectors here, there's something special about it. You might not notice from the picture, but they are actually, the round connectors are smaller than a regular type of BNC connector. And actually they are triaxial type of connectors. So you can have like balanced signals on them. I would like to have to try them out, but they are prohibitively expensive or so. They seem to cost at least 50 euros as a separate connector, or hundreds of euros as an assembled cable or so. I mean, I couldn't find anything for a reasonable price, but this is a kind of an interesting type of connector they're using here on the device. And also in this unit, when we open it up, we got a staggering amount of relays. I think I counted 37 relays. And why is all that there? Well, one of them is that each of these connectors can be switched between the data communication equipment and the data termination equipment mode. You still might know that from RS-232. Might switch between the balanced and the unbalanced mode of operation. You can have selectable line termination characteristic from the menu of the device. Between the D-sub connectors and the twin-X connector, and the loop back function for self type of testing. So I assume that all these relays are there basically to offer all these possibilities here. Now there's another interface here, which is the ITU V35 modem connector. That once was an important connector, I think, in the telecommunications world itself, but not so much for private type of use. Now I would say it's completely extinct. But the connectors are massive and huge. So here you see the connectors that were shipped with my device, incredible in size. It's yeah, it's another time really. Yeah, and this is the only interface that I additionally ordered from eBay. It's the lab interface, and this is the interface that actually offering you simple TTL outputs and inputs to the device. So this is where it gets interesting if you want to hook this device up to other measurement equipment. You can do that to quite some degree just using these test points, etc. But in order to have a true TTL input without having been stuck to, say, RS-232 levels or complex type of telecom protocols, you'll probably want to have here this lab interface. And it got quite a couple of buttons on it as well. It's interesting because it can run in unipolar and bipolar mode. It can also run in balance modes, and we'll explore this a little bit more. We also got termination settings there, and clock direction settings and so on. So that's a kind of a useful interface I have, I think, if you want to use this in your laboratory. One thing that I don't have, but if you really have a lot of interface and you're regularly using them, there's also an external unit where you can connect up to 4 interfaces, and via the software of the device you can select which interface you're working with. Alright, this brings us to the end of the first episode of this review. In the second episode, which we'll be posting hopefully a few days after I finish this first episode, we're going to do a lot of hands-on testing. So we're going to do testing of actually generating and analyzing bits, like bit error rate type of analysis. We're going to explore an E1 interface and inserting data streams in it, etc. and picking them out again. We're going to explore voice calls over the device. We're going to do jitter analysis. We're going to do ASCII character generation and other things as well. So stay tuned for that second episode. Thanks for watching. Do subscribe to the channel and give this video a thumb if you enjoyed it, and see you next time.